Hey guys, more practice here with sequences, and for this one we want to take a given situation and make that situation to a table and then write the explicit formula to represent the situation and then see if we can graph that, the table and the sequence and the formula. So in this scenario I'm going to give you a little example, and we're actually going to have bacteria. And one thing about bacteria that we know is that they like to grow, and they like to grow pretty fast. So let's say that initially in this little specimen that we're studying, we have 3 little bacteria. And then let's say 1 hour passes by, and we'll say after the first hour, now we have 6. And then let's say after the second hour, now we have 12. Alright, so here we have these 12 bacteria, and then after the first hour we had 6, and over here we had 3. And let's take this situation and represent it using a table, then we'll write the formula, and then we'll actually show the graph. Alright, so filling out the tables is with these sequences is somewhat, I think, the easiest one. The left side for term number, we always start with the first term, and we just go by ones. So we want to look at the first term, then the second term, and then so on. So in this case, the first term of the situation, we need to think about what happened after the first of whatever we're talking about. So in this case, it's going to be a lot of kids think that 3 is what actually goes here, because they're saying, oh, wasn't the first thing that we looked at, we saw 3 bacteria? And yeah, that's true. We started with 3, but after 1 hour, after the first hour, how many did we had? And we actually had 6 after the first hour. What this 3 is, this would be your initial value. This would be if 0 was on the table, right next to 0, it would be 3. But we're just looking at what the first hour was. And we had 6 bacteria after the first hour. In the second hour, we had 12. So maybe it's a little difficult to tell what's going on here. If I write down the list, the sequence down here, 3, 6, 12, maybe it's easier to tell that in this case we have a geometric sequence and we're actually just multiplying by 2. So if I were to continue this pattern, 6, 12, 24, 24 times 2 is 48, 48 times 2 is 96. So here we have a geometric sequence with a common ratio of 2 and a first term of 6. Even though we started with 3 bacteria, after the first hour we have 6. So if I asked you to write the formula for this sequence, for this table, remember we have a geometric sequence, so we would have to look at this one, and we have to plug in the first term, which we said was 6, and the common ratio, which we found to be 2, because we saw that the pattern was just multiplying by 2. Right, so we had 3, 6, 12, and we continued that pattern to get 48, or 24, 48, and 96. So my formula is going to be G sub n equals, and my first term is 6, my common ratio is 2, and n minus 1, make sure is written as a little exponent. So here's a sequence that represents this table. And here's the formula that represents this table. And notice how these two really say the same thing. They just say it in different formats. Here they give you all the values. Here this tells you, hey, we start with the number 6 as our first term, and then after that we're just multiplying by 2. And then in terms of the graph, You can think of your table as really like X, Y's, inputs and outputs. And you can graph the term number on your x-axis and the term value on your y-axis. So the first one is 1 comma 6, roughly right there. 2 comma 12, about there. 324, 448. So I'm just graphing these points. And then 5 comma 96. And what you see here is that we start to get really, really big over here. If I were to connect this and make this curve, this is actually an exponential function. So these geometric sequences make exponential functions.